the title is Modular Representations and Perverse Sheaves on Affine flag Varieties. And it's basically a continuation of Laura's talk yesterday. So it's based on joint project with her and Simon Riche. And I'll be mentioning things joined with other people. I'll mention those people then. So the setup will be what Laura introduced. So I'll start with a say reductive group, and then I'll take the flag variety. So I take like F will be the local field, and we have this loops group that Laura, I mean technically GF of K, that Laura talked about, and then we have in this GF we have GO, the group of positive loops that contains the Iwahori, and then we have the affine flag variety, which is coset space, as she mentioned. And then we are interested for some reasons in the category of constructible category of Iwahori equivariant sheaves on these flags. And with coefficients in some field. So with coefficients in a field, well, say capital K, and of possibly an L, sorry, characteristic of capital K is L more than 0 much of the time. And so just to refresh your memory of Laura's talk, let me mention, like just recap the result that she explained. Yeah, K is a field of characteristic 0, so small k is characteristic 0 field, algebraically closed. And such is capital K as well. Okay, so someone was asking what's GO, and GO is the group of positive loops. So or is the, I'm going over it quickly because it was mentioned in the talk yesterday. So all right, so yeah, so we're interested in this category of constructible sheaves. So this is the affine Hecke category, or categorification of the affine Hecke algebra. So what do we want to say about it? So the first thing we want to say about it is the what Laura already said, namely if we consider so first a recap of Laura's talk. So we consider the quotient which I want to say uniquely reducible, although that will be accurate only if G is simply connected. So P maybe, so that would yes, maybe I'll abbreviate perverse I on the flex to pi, and then I'll take the quotient. So it's just a CR quotient where we kill all irreducible objects, kill all irreducibles whose with positive dimensional support, whose support has a dimension at least 1. So explicitly, the irreducible objects in this thing are indexed by affine Well group, extended affine Well group. Extended affine Well group. And then we'll just, so pi0 is pi modular the subcategory generated by all positive length. I mean, all objects whose label corresponds to an element of positive length. And then, so remark is that, so di of flags is a monoidal category, but of course, I mean, if you've ever seen anything like that in the affine or fine dimensional setting, you've noticed that the convolution here is like that is never exact. So the perverse sheaves are not closed under the convolution. Yeah, so maybe under, maybe I should say under convolution. So this is my wife's device, so you'll see her notifications. So under convolution, that will denote by star. And so we are lucky here because once we are left with this sort of point objects, so when you can evolve to point objects, nothing much happens. So convolution, this quotient is exact. So this induces a T-exact convolution. Convolution on di of flags modular this ICW, which we naturally will call di0 of flags. And so this quotient is a monoidal abelian category. And then, so the theorem that you may be hearing for the second time in those 2 days is that this pi0 is equivalent to representations of z of u in G check. So where G check is the Langland's dual group, U is a regular unipotent. And so, yes, there are some assumptions on characteristic that I will not repeat under. So maybe I'll just summarize this as saying that L is not too small. Okay, so I want to say a few words about the idea of the proof, and then most of the talk will be about the context and applications and generalizations. Yeah, so some ingredients that Laura described, I will just recall briefly. So this is based, so proof is based.
Roman?
Yes.
Juzu asks, what's the fiber functor for the left-hand side for the pi0?
Well, there are two answers, and sort of, there is the answer I want to give, and then there is a more honest answer. So the more honest answer is that you don't really need to construct one, because you can just formally rely on already known Satake equivalence and then just proceed from there. But there is a nice geometric model for this fiber functor, and which, I would like to see developed more, in the sense that maybe it's not commutativity constraints and various tech. There are things that you want to have from the fiber functor may not be worked out in this approach, but so the answer is that this is kind of generic vanishing cycles at 0. So a description of the fiber functor is phi. To simplify the wording, I'm assuming that G is simply connected. That can be easily avoided. Phi at sort of 0 for 1. G simply connected. Well, this is generic vanishing cycles. Okay, thanks for giving me a pretext to mention this. Okay, so yes, proof is based, as Laura explained, on the central functors, on Gates-Curry's central functors and Gates-Curry. It's just one relevant Gates-Curry. Gates-Curry's central functor and monodromy. So it's obtained by cycles, and there is monodromy automorphism, something I don't want to focus on. So this by Tanakian formalism allows one to show that this pi0 is representations of some group. Let's call it H. Of course, there is it's based on Satake equivalence, but that's everything in this subject is based on Satake equivalence. But then, yeah, so central functions monodromy automorphism, which allow by Tanakian formalism to deduce that this category is representations of H, where H is subgroup in G check. Which is commuting with U, which a priori is some unipotent element. So yeah, I see Sasha's question, and there is an easy answer which I will give later. So yes, so then I want to focus on the following two aspects of their argument, and so we need to check. I mean, not focus, just mentioned. So I need to check that first that U is regular, and then second that H is the centralizer of U. And so this is something that Laura kind of briefly mentioned, but maybe I just want to add a few more words there. So first, so remark that so all this has been done earlier for characteristic zero coefficient, that one in characteristic zero can and has been checked using Frobenius weights somehow, and the fact that have nearby cycles, and then monodromy filtration equals the weight filtration. So there's some non-elementary and deep theorems of this nature that were used there, which do not whose analog in positive characteristic is not available to my knowledge. So we really need a different argument here, but one can do a little geometric argument, and so so it doesn't work in a characteristic L. And so so what do we do here? So instead, we, using these Wakimoto sheaves that Laura talked about, we produce a filtration that kind of mimics, or eventually is identified with filtration by weights in a different sense, indexed by weights of the maximal torus of G check. So this filtration somehow, as a centralizer of regular unipotent is contained in Barrel, and as a module of a Barrel, our affine dimensional module has the filtration indexed by weights, whose particular terms were appeared in Riche's talk, I guess, or maybe not exactly. But okay, so we produce filtration index by weights, and then pass to subquotient corresponding to just a pair of weights, nu and nu plus alpha, where alpha is a simple root, and then check that monodromy is non-trivial on this subquotient, and there somehow shows that the monodromy is kind of lies in some Barrel, and it gives a has non-trivial projection to every simple root, which every simple root subgroup, which surely implies it's regular. So this implies regularity. Okay, so I just wanted to mention this little geometric argument, but now, so the next point is, so H is actually equal. So a priori it's now subgroup here, but we want to actually check that it's equal. And here there's something that also will enter the applications, and I want to talk about. So,
Roman, a quick question.
Yeah.
So you're trying to prove something about, like you're saying you're showing something as a Wakimoto filtration. Are you trying to show something about any object in the category, or just?
No. There is something that is checked pretty much in the same way in characteristic zero in this modular setting, is that this central sheaf assume auto filtration.
Okay, sure.
So yeah, sorry, it's throwing this under the rug. Other questions? Okay, so right, and so here we use the following things. Here we use that again, something that has been known in characteristic zero and it proved in a similar way here. Use that if we consider the projection z of some m, say. Okay, so it's in this pi of x. But now I want to introduce another gadget. So another category, this Ivachori-Whittaker category of x. So this is inside d of g mod I minus psi, where psi is this character, which I think Laura mentioned. So we have Ivachori subgroup, and then we have kind of I and I minus are both in G4. And we have some character of I minus coming from the character, additive character, and satisfies some non-degeneracy conditions. It's not non-trivial on the simple root subgroup corresponding to the finite root, and trivial on the one corresponding to the infinite root. So this is some sort of approximation to the Whittaker category for the experts. But in any case, so there is this thing, and so there is a functor which behaves nicely. It kills some irreducible objects and sends other reducible objects to an irreducible. So we can maybe, so how should I draw this? Sorry. I'm trying to say that this goes to gi of m in here. And there is this little lemma that giw of m is tilting if m is tilting, which is again vacuous in characteristic zero case, but it's of course a strong condition in the modular case. And then, so why does this help to establish the theorem? It's because, so for tilting for T1, T2, I mean, first there is this diagram, so we have this pi of flags. So this, don't remember if Laura mentioned this in this form, but so the projection factors, but also for T1, T2 tilting in, well, say here, then we have on 1T1 to T2. So basically this projection factor by exact replication of Zorga's method, this home is maps isomorphically to home in pi 0. Sorry, in home in pi 0. I'll omit the projection from annotation, but hopefully it's clear. Or maybe, okay, maybe let's write this way. So the bar denotes to, so if I have here some F, then it goes to F bar.
Roman, would it be possible to take the 5-minute break now, or is it?
Yeah, I think that's maybe a good point. So this I'm done talking about the ideas in the proof of this theorem, but now I will pass to applications and generalization. So maybe yes, that's a good point.
And there's a couple of questions, one from Ben Elias and one from Elijah. Do you want to say you can unmute yourselves and say your questions?
I already asked mine.
So no, I mean about the image of the Gersgeris functor. So one can show that the image of Gersgeris functor actually is the full thing. It generates the category because every object in the category has a tilting resolution, and then we know that this central sheaves are essentially tilting, and every other tilting is a subquotient, something like this. Based on this, you can show this. Yes,
Every zero-dimensional object has a resolution?
No, every object, I mean, sorry, I misspoke. Not a resolution, but how it's called. I mean, it can be presented as a complex. It's quasi-isomorphic to a complex of tilting objects. So in particular, it's a subquotient to a tilting object. And then from there, and so somehow the central sheaves are essentially tilting, and we have enough tiltings of that form, so that allows.
How are you going to get? I'm just trying to think about this in the case of A1. Like, I know what your standard gate square central sheaf looks like. I mean, you've got the trivial rep, so you've got the monoidal identity. You've got the standard rep, which has both the BS and BT, if you will, these two simple reflections in affine type, as appearing inside it. How are you going to get just BS resolved by gate square central sheaves?
BS meaning just the maybe we can discuss this later.
Okay, I'll ask you.
Have this example.
And Elijah had a question.
So does it depend? It probably does, yes, because I mean the proof is not super conceptual. I mean, I think it just repeats the proof in the characteristic zero case, which you just prove it by hand for small irreducibles, and then check that it's I mean, minuscule and quasi-minuscule, and then
you have to.
And then you just it's invariant under. It's preserved under convolution, so yeah. But yes, you want this minuscule and quasi-minuscule to be in the fundamental alcove, and things like that. So there are some restrictions on P which this statement requires. Maybe they are. I don't know if they. I mean, there may be weaker assumptions than needed for other. Oh, maybe I should have said that this idea. I mean, it comes from. It is a generalization of something in characteristic zero, and about characteristic zero, the idea was essentially due to Mishra Finkelberg, who pointed out to me that the central sheaf should be, well, because also dual, at least that the center is invariant under Horo-Matsumoto involution, and then the statement is direct. It's causal dual to the fact that when you push forward central sheaves to the Grassmannian, or convolve with the constant sheaf on G4, then you get irreducible sheaf, which is kind of part of the immediate from the construction. So yes, I just wanted to mention this attribution. And somehow this fact that so by now, I mean, causal duality in this context was constructed in our paper with Jiwei, but the fact that the central sheaves are causal self-dual, I don't think anybody has checked it. I mean, it's no doubt this is true, but it's kind of would be nice if someone was motivated to do that.
In type A, Mackie and I can like check this.
That's great.
Oh, we haven't written it up.
That's great.
Sam Raskin has a question. Sam, do you want to ask your question?
Yeah, I just sent it over the chat, but Roman, just as a stupid thing to make sure I'm following it all. So if I consider the same quotient category,
that's right. Yeah, that's right.
just,
I mean, there is, of course, there is another version where you get like Jordan modules, and here there is also such a version which is needed. I mean, which is not in the existing paper, but will be the next one. The short answer is yes.
but then it wouldn't be monoidal anymore, I guess.
No, it will be. No, from this perspective, it doesn't matter. It's just the objects are the same and the exactness properties are the same. It's just what. Oh, sorry. No, you are correct, but yes, there will be a little bit. Yeah, you're correct. There will be a little bit of non-exactness, but very controllable. No, good. So should I restart?
Go ahead.
Okay, thanks. So yes, and then just maybe one. So using this plus plus dimension counting argument, conclude that H is equal to the whole Z of U. All right, so now there is a list of applications. Which looks like I will not be able to talk about all of them, but let me at least give you the list. So there is this unipotent by Whittaker category and derived Satake in positive characteristic. So this is with Dima Arinkin. Then this is full equivalence. So maybe equivalence between two geometric realizations of the affine Hecke algebra. So equivalence the I of flex to the check of the Steinberg variety and Harishchandra and modular Harishchandra by modules which is, I think it has some relation to Sam's talk. So, but yeah, maybe I'll say a few more words later. And so as an application, this is what's called Finkelberg-Mirkovic conjecture. And then the most interesting things are unknown. So then questions on P cells and cohomology of high Frobenius kernels, which are appearing here. But okay, I hope to get to this in the end. Okay, so so let me start with this first item. So I have 5 minutes for each one. Just going back to this previous statement that from so what was my notation? So yes, I introduced, yes, this is Z Wahora Whittaker is of T1 to Z Wahora Whittaker of T2. So where T1, T2 are modules over the dual group, which happen also to be tilting. So we said that this is isomorphic to home from to home from T1 to T2. Well, sorry, maybe I should first rewrite it as home over the same thing with bars, which is, remember, the projection to in Pi0. But then I can further rewrite it by the previous theorem as home from T1 to T2 over the centralizer of the regular unipotent in G check. And then finally, I want to suggestively rewrite this as, well, home over the kind of G check of U, sorry, home in the category of equivariant coherent sheaves just by Frobenius induction. In coherent sheaves, G check equivariant in the orbit of that U from T1 tensor OR to T2 tensor OR. And finally, this is the same since the regular unipotent orbit is dense in the set of unipotent elements, and its closure has codimension 2, and everything is normal, and life is good. Then it's the same as home in G check of U, where this is the set of is G check, the set of unipotent elements. From T1 tensor OR to T2 tensor OR. So, sorry. Right. So, and then also high X from tilting objects vanishes, fortunately. So from this, we see that the kind of span, just the full subcategory generated by these things, it's, it's also the full subcategory. It's identified with the full subcategory in the G check of U. Well, this is kind of nice, but maybe not too nice, because you kind of have a somewhat artificially looking category, which and then you have some strange subcategory. So it would be nice if we could say that these tiltings generate something natural, and then this natural thing would be identified with something on the dual side. And indeed, this particular tilting, so again, all tiltings generate the category, so this is the highest weight category, but these are not all tiltings. So I haven't discussed in detail, but here the simples are indexed by essentially weight lattice, and these things correspond to dominant weights or something like this. But you can consider the following thing. We can consider the averaging functor from this thing. So, you know, we introduced this Horowitz-Whittaker condition on one side. Why don't we introduce the same condition on the other one? So this is something that I kind of was afraid to do for some reason when I worked on these things in characteristic zero, but now I think that it's a good thing to consider. And so this so easy claim. So this is the averaging function again. That this Ti is ZIW of T generate the kernel, generate orthogonal to the kernel, orthogonal left, or I think both left and right, to the kernel of this functor. And well, corollary, so of course there are many technical details I'm skipping, and we also need relying on a monodromic version that monodromic version of the theorem, but that's, you know, so if you look at the paper on the archive, it says something something 1, and this will be hopefully something something 2, hopefully later this year, of the Pi0. Is that if we just consider, so if we write WH to be the full subcategory generated by the image of this functor, then this is coherent sheaves on G check. I mean, derived category of coherent sheaves on G check, supported on U. So this is kind of a nice answer. So these are essentially coherent sheaves on the stack of flankless parameters that we like to see. See, how much time do I have left? Okay, I'll
Maybe 10 more minutes.
Oh, 10 more minutes. Okay.
Or 10 or 15 minutes.
All right. So maybe I'll make it 15. So, so corollary of this with Arinkin is D of G of O of Grassmannian is monoidal category. Sorry, maybe I'll write it this way. GF mod GO mod GO is so derived decoh like G check of this derived scheme. And so I should say that this form of answer, so answer was suggested long ago by Greenfield. And in some form, we worked it out in characteristic zero with Misha, Finkelberg, but those methods do not apply here. And so basically the idea of proof is, goes back to something I learned from my algebra high school teacher, who was telling me that, who was kind of ridiculing the students who misunderstand the concept of a multiple root. And he said that those students say that, you know, a multiple root is when you plug in the number and you get 0, and you plug it again and you get 0 again. So, but this kind of becomes the exactly the right approach here. And so basically the reason we have this answer is that this Satake category leaves over the trivial Lagrange parameter, and it leaves its it does so both on the, if you look at it sort of on the left and on the right. So in slightly more concrete term, slightly more concretely, we can say that D, GF or G or maps to endomorphisms over this Whittaker category of the category of D of GF modular G or, so in modular I minus psi. And so this category here, so Whittaker we already discussed, and this category is equivalent to, again, just derived category of representation, so G check, by a paper of myself with Dennis, Ivan, Mirkovic, Laura, Simon and Laura. That's right, and then myself. So this paper on the archive from several years ago. Okay, so that's okay. So okay, am I still, do I still have a little bit more time, or what's the?
Yeah, let's give you well, at least another five minutes. Okay.
Okay. Yes, 5 minutes is okay. Okay. So okay, so I don't have much time to talk about the other applications, but so maybe I just want to mention. So based on this and monodromic version of these results, we are one can check this using this plus, well, again, some version of Zorga's method. So the method again is different from what has been used in characteristic 0 or it is technically different. Can deduce, so that's, I don't know if it will appear this year, but hopefully it will appear eventually, that maybe under more restrictive assumptions, and in particular will identify kind of G check will have to be equal to G check as G check varieties. Near completed at a new point. Set. So yeah, so we can deduce that D, say, I of flex should be the same as derived category of coherent sheaves on this fiber square of cotangent bundles. So again, this is a direct analog of something that's known in characteristic 0. But then there is an additional thing that this is equivalent to that I want to say. So this is derived category of G plus G, comma G modules, so just Harish-Chandra modules with a fixed infinitesimal fixed Harish-Chandra central character. And the interesting thing here is that this composed equivalence has nice exactness properties. So this is T exact up to, so this all leaves over an important cone up to shift by half codimension of an orbit on subquotient corresponding to the orbit. So this is kind of an orbit. This is a perverse coherent shift. So, yeah, this is. I think that a quantum version would be interesting to compare a quantum analog should be compared with, you know, should be related to FLE, but and its ramified version that Sam discussed. So I just wanted to mention this connection. But okay, so I should be wrapping up. But so I just want to say one more thing. So corollary, I mean, if you just look at things which are sitting over the zero orbit in the previous page, then it's going to be T exact. And then, you know, working with a billion categories, you can embed G modules into Harshchandra modules. And so you can just see that G check modules, well, so it's zero. So this means regular block is equivalent to perverse sheaves I0 equivariant complex, where this is radical of Ilahori. And then, so I just want to finish with one sort of observation that corollary is that this G or on Grossmanian acts on the derived category of this principal block. Now, so similar action in the quantum case has been related. And yeah, using the description of the left-hand side that I talked about, one can also give direct algebraic construction of this. But so a similar action in the quantum case is related to calculation of the cohomology of the small quantum group, which is here is interpreted as axed from, well, the unit object in perverse sheaves on Grossmanian to Satake of G04. So this is something that's discussed in my old paper with Sergei Arkhipov and Viktor Ginsburg. And somehow and both these things are identified with functions on the nilpotent column. And basically, if you want to identify directly the right-hand side with this answer of n, then by Tanakian formalism, this is related to sort of can construct a map in one direction, starting from like C1 of the determinant bundle, which provides a tensor endomorphism of things of the natural sort of fiber functor over this ring. But now I just want to say that in this modular setting, one can also look at cohomologies of higher Frobenius kernels. And this will be related to X from delta E to Satake. Oh, sorry, there was a typo here. It's not Satake of G04, it's Satake of G. Maybe to be on the safe side, I'll say it's related to. So to the Satake of functions on G Frobenius twist by R. And these are, again, well, related to functions on NR. So these are R tuples of commuting importance. So this is, well, it's Friedlander-Suslin. So my hope is that just this can be constructed geometrically using, so here we have tensor endomorphism, and some other, so if I call this C, then there is some divided powers of C which exist by, so cohomology of the Grossmanian has divided powers by calculation of Yun and Zhu. So basically, I conjecture is that this divided powers can be used to construct our commuting idempotent endomorphisms of the corresponding fiber functor of this ring, and then connect this to this calculation of cohomology of redundant and Susland. And again, in the quantum cases, is related to the tensor ideal in tilting modules as in Humphreys conjecture, a quantum version of Humphreys conjecture. And there was a recent paper by Hardesty, Chair Hardesty and Riche, which partly extended this theory to the modular case. And so I hope that this picture would help to connect this to cohomological support and sort of high analogs of Humphreys conjecture. Okay, so maybe I'll stop here.
So maybe we have time for a few short questions. I put the information about the lunchrooms in the chat. So if you like, you can head to the lunchrooms now or whenever you like, but if other people can stick around here to ask Roman some questions. So. Go. There's a question from Thorge Jensen.
Yes. This has to do with this paper of Pramod, Will Hardesty, and Simon Riche. So they say, I think they prove maybe under some restrictions that these P cells, antispherical P cells, as they say, so they correspond to ideals, tensor ideals in the category of tilting modules. So now, so tensor ideals in the category of quantum group of tilting modular quantum group at relative unity, they correspond. I mean, they're in bijection with nilpotent orbits in the dual group, and one of the constructions is by just taking cohomological support or for some tilting for tilting modules with dominant labels, just cohomology. And now, so this Pramod, Will, and Simon, they kind of devise some procedure to construct a sort of sequence of commuting nilpotents from a P cell. And on the other hand, these sequences of commuting nilpotents, they appear in the description of cohomology of high Frobenius kernels. So natural conjecture is that, this is bijection between injection from the set of P cells to sequences of commuting nilpotents, and then so that the cohomological support, so in the sense of taking cohomology of the high Frobenius kernel of a tilting module is it's compatible with that. But yeah, I think this is very conjectural at this moment.
So Roman, I was wondering, will your proof with Dima also give a description of this restriction functor on the coherent side to a Levy in terms of the constructible side?
Yeah, I think so. I mean, frankly, I haven't, although I know you care about it. Yes, I haven't thought about it specifically, but I think that should be possible. But yeah, we can discuss it at a later time. I mean,
Okay, thanks.
I think it should work, but yeah.
So I just wanted to say we're gonna start up the lunchrooms in a moment. I don't think people have to leave the main call right this instant, so people could ask Roman a few questions, but the AV staff are gonna wanna close it at some point during lunch, just so they can get the recordings, and so we'll have a chance to test out the afternoon speakers. All right, so no rush, but I'm gonna go try to set up the lunchrooms, and so.
So I see Thorga is following up on his question, but I'm not sure I understand this, and we can maybe discuss it later. I mean, I'm not sure I understand what. Thorga, I'm not sure I understand what you're referring to.
Hi, Roman. I have a question.
Okay, hi.
So you mentioned like with this equivalence between the Hecke category and then the coherent sheaves on the Steinberg variety, and this would sort of somehow relate to these Harish-Chandra modules. And there you said if you write down that equivalence, then that would be T-exact, taking the perverse T structure to the, I guess, a shift of the natural T structure.
Mm-hmm.
For the Harish-Chandra bipolar.
Because I mean 7 a.m. is brutal. Yeah, it is brutal. Yeah.
So
my question is, if I now move that T structure to coherent sheaves on the Steinberg variety, is there a natural way to describe the T structure in that category?
yeah, I think it's some version of this exotic thing. So
yeah. So what does that mean there?
well, I mean, I think again you can characterize it. So okay, so maybe one other way to think about it is in terms of this non-commutative Springer resolution, and there is some algebra writing things so that there is some non-commutative algebra like A, which exists in with some finite localization of Z, and so that the derived category of A is dB coh. There are two versions, but in the monodromic version, we should do this, so we can just do this. And then, if you accept this A, then I mean there is a nice answer, namely it will be something like, I think Harish-Chandra modules will be just kind of A bimodules. I mean, okay, so if we complete with the central character, then it'll be like A times over all of G. Supported like N. Yeah, now so how to think about this A? I mean, again, it's, I don't know, a very kind of explicit way, but you can characterize it as projective. I mean, endomorphism. So A is like endomorphisms of E, where E is this tilting bundle, and it's the projective generator for the heart of the only T structure, which is break positive, and some normalization, satisfies some normalization axiom. So yeah, I think this is pretty much parallel to a characteristic zero. So one sort of observation about this is that in a way, there's this because this relation of G modules and positive characteristic to the tangent bundle, its deformation G tilt comes from localization formalism, but kind of in this earlier versions in this BMR, we had this nuisance that you can identify modules with a given general central character with coherent sheaves, because like there's a zoom algebra which splits on the neighborhood of the fiber. But if you sort of want to talk about all modules without fixing a central character, say P central character, then there's some algebra that you have to, as a non-trivial class of the zoom algebra that you have to take into account. But here, when you sort of, roughly speaking, when you work with these bimodules, then there's this job coming from the left and from the right, and it cancels. So somehow it's more neat formulation. Okay, so maybe we should move to the.
But what is the relation between these Harish-Chandra bimodules and the
Laura, did I answer? Misha, just wait a second. So did I answer your question? Or?
Not exactly. I was asking if there was sort of an intrinsic definition of this T structure just in terms of coherent sheaves on the Steinberg.
Well, there is a characterization. So this is unique to structure for which the braid generators act in the right exact way, and then there's some normalization.
Okay, okay.
Direct image. Say what happens under direct image to N. But that's as explicit as I know.
Okay. All right, thank you. And thanks for your talk.
Yeah, thanks for your talk, yes.
But what is the relation between these Harish-Chandra bimodules and the ones in Satake, equivariant for loop rotation?
Yeah, I don't know. And I mean, so I want to say causal duality, but maybe I'll say later. But
thank you.
Roman?
Yes?
On your last page, you mentioned about the cohomology of height Frobenius kernel and also with this X. So, yes. And how is the multiplication? In cohomology, you have a cup product. How is the multiplication reflected on the right-hand side?
Right. It's coming from the fact that this thing like so actually here there is of course a type of Satake of O of G. So I just take this functions from the group and well, it's infinite dimensional, but it's like a module for the algebraic group, and it's an algebra object in this tensor category. So using this algebra structure, we can make like this thing into an algebra, and similarly here.
Okay.
So in the quantum case, this is discussed in detail in this paper ABG, but this is not. I mean, this.
So that corresponds. That will correspond to the cup product on the cohomology ring. Okay, thank you.
And I also wanted to ask you, so when you have this Frobenius kernels, then saying that you get functions are tuples of dimensional potents, but that thing by itself has nothing to do with characteristic P. So should there be some kind of version of this all of the functions on the variety N R, geometric construction of functions on this variety N sub R, which sort of makes sense in characteristic 0? Is that expected or not?
No, I mean, you can write it down, but it's not. I guess the short answer is no, but yeah. And I mean, yeah, there are different things to say here, and maybe I kind of made the picture more rosy than it is. So in particular, the cohomology algebra is for G1, and in the quantum case is well known, Friedlander partial and Ginzburg-Kummer respectively. But for this high Frobenius kernels, it doesn't look so. The theorem of Friedlander and Suslin, it only describes the spectrum as a sort of variety.
Homeomorphism.
More or less up to homeomorphism. There is no explicit answer as to what this cohomology, explicit generation relations, and I don't think I don't think one expects it. It's kind of somewhat messy. So what this approach should give is, there's a map in one direction between some explicit algebra like functions on commuting variety and this cohomology. Maybe even maps in two directions.
You want to get the commuting variety, this kind of nilpotent commuting variety, or kind of high nilpotent commuting variety. You want to get some geometric construction of it, right? But
no, geometric, yes, but I'm just saying that. Okay, I can write, like this thing that I wrote here, and this is a geometric construction of maybe cohomology. I don't know if you call it exactly geometric, but this is some model for cohomology of higher Frobenius kernels, but this Sanakian formalism, if you use this commuting importance, then it gives you a map in one direction between functions and commuting variety and this thing. And this map is not going to be an isomorphism, although it will induce a homeomorphism on the spectrum. So I think what is there is that there are maps actually in both directions, but their composition is not identity, but maybe some sort of Arth Frobenius or something like this. So it's raising a function to the power p to the r, which is a bijection spectrum, but
it's up to a isogeny of
yeah. It's kind of, I would say rather it's opposite to isogeny. It's like up to.
But I'm confused. But do you in principle see how R tuples of commuting important elements arise, or do you not see that?
Yes.
Sorry?
I think I do, because so in this picture I want to say that they arise from this elements in cohomology. But
I see. And this element, so I'm confused. This element, this C brackets P. So what degree does it have?
Yeah. So C has degree 2, and
Yes.
this degree, this is degree. So if I write degree here, so this is 2, and this is 2p. This is 2p squared. It also should be related to X between Frobenius, self X of the Frobenius twist functor. That's another story.